Tutorial 3, Principles of Flight. This flight training tutorial will discuss key principles of aerodynamics of flight. In order for a pilot to safely execute maneuvers in flight, it is important to understand the aerodynamic forces acting on an aircraft in flight. Although there are various kinds of pressure, pilots are mainly concerned with atmospheric pressure. It is one of the basic factors in weather changes, helps to lift an aircraft, and actuates some of the important flight instruments. These instruments are the altimeter, airspeed indicator, vertical speed indicator, and manifold pressure gauge. Air is very light, but is still affected by gravity and acts like a fluid by exerting force in all directions called pressure. At sea level, the average pressure exerted by the weight of the air is 14.7 pounds per square inch and is measured as 29.92 inches of mercury, or 1013.2 millibars. This is the standard pressure. If the pressure is anything different than standard pressure, it is called non-standard pressure. The standard atmosphere at sea level is a surface temperature of 59 degrees Fahrenheit or 15 degrees Celsius and a surface pressure of 29.92 inches of mercury or 1013.2 millibars. A standard temperature lapse rate is one in which the temperature decreases at the rate of approximately 3.5 degrees Fahrenheit or 2 degrees Celsius per 1,000 feet up to 36,000 feet. Standard pressure lapse rate is one in which pressure decreases at the rate of approximately 1 inch of mercury per 1,000 feet of altitude gain to 10,000 feet. Standard atmosphere is used to calibrate aircraft instruments. Therefore, when the pressure changes to a non-standard pressure, the aircraft's instruments must also be recalibrated within the aircraft by setting the outside pressure value or by correcting until the altimeter reads the airport's elevation. To read pressure altitude, set the altimeter to 2992, and what is read is the pressure altitude. Density altitude is simply pressure altitude corrected for non-standard temperature. The aircraft's performance is affected by the density of the air, so this value lets pilots take steps to account for the difference in engine and aircraft performance. The air density can be affected by pressure, temperature, and humidity. The higher the pressure, the more dense the air is. The lower the pressure, the less dense the air is. High temperatures cause air to be less dense, and cold air is more dense. And high humidity causes less dense air than low humidity. There are three basic theories that allow us to explain how airplanes fly, the first being Newton's laws of motion. Sir Isaac Newton developed three basic laws of motion that describe how objects interact with each other. The first law states that objects at rest tend to stay at rest until acted on by another object. So, an airplane sitting on the ground needs some force, propeller, jet engine, etc., to get it moving. The second law states that force equals mass times acceleration. This allows us to see how much airplanes accelerate from the force of an engine, or how fast they can stop. And the last law of motion states that for every action, there is an equal and opposite reaction. On an airplane, if the propeller is pushing air back, the air is acting opposite and pushing the plane forward. Also, the wing pushes air down, which causes the air to push the wing up. The second theory that helps explain lift is the Magnus effect. This theory was created by Heinrich Gustav Magnus and helps show how the wing functions. When a cylinder rotates in a fluid, it creates a movement of the fluid because air molecules actually adhere, stick, or cling to the surface. When the cylinder is rotating through a moving liquid, part of the liquid is moving fast over the top, and on the bottom, the liquid is slowed down because of friction with the cylinder's surface. As shown above, At point A, a stagnation point exists where the airstream impacts on the front of the airfoil surface and splits. Some air goes over and some under. Another stagnation point exists at B, where the two airstreams rejoin and resume at identical velocities. When viewed from the side, an upwash is created ahead of the airfoil and downwash at the rear. Magnus's research shows the basic principle that a wing causes air to move faster over the top and slower over the bottom of the wing, causing a higher pressure at the bottom of the wing and lower pressure on the top of the wing. This low-pressure area produces an upward force known as the Magnus effect. The last theory of lift is Bernoulli's principle. Daniel Bernoulli explained that the faster a fluid moves, the less pressure the fluid has. As with the Magnus effect, faster moving air flowing over the top of the wing causes a low pressure area, causing lift. An airfoil is a structure designed to obtain reaction upon its surface from the air through which it moves. By looking at a typical airfoil profile, such as the cross-section of a wing, one can see several obvious characteristics of design. The end, which faces forward in flight, is called the leading edge and is rounded. The other end, the trailing edge, is quite narrow and tapered. The chord line is a line drawn from the very front of the leading edge to the trailing edge of the wing. The chord line cuts the wing in two parts, an upper and lower half of the wing. Each half of the wing has what is called a camber. This is the general curve shape of the wing. The greater the camber, the more curved the wing is. In the diagram, it is clear that the camber of the upper surface is quite more pronounced than the camber of the lower surface, which is almost flat. Different airfoils have different flight characteristics. For example, the scooped-out bottom of the early airfoil gives lots of lift, but is not streamlined and is not stable at high speeds. The laminar flow airfoil is an almost symmetrical airfoil that is more streamlined but does not produce as much lift. The middle designs give some combination of the scooped-out bottom and symmetrical designs. Airfoil designs that are perfectly symmetrical, like the circular arc and the double wedge airfoil, are used on many high-speed planes and solely rely on their angle of attack to produce lift. These airfoils provide very little aerodynamic resistance and are stable at high speeds. To review, angle of attack is the position of the wing's chord line relative to the wind that is hitting it. For a wing in a normal angle of attack, the wing splits the air so some flows over and some air flows under the wing. The air flowing over is pushed faster, and when looking back at the theories of lift, we know the lower pressure created causes lift. Also, the air that flows under the wing hits the bottom of the wing, causing the wing to be pushed upward. If the wing is subjected to a different angle of attack, the airflow over the wing is changed, causing the forces to act in different places, and the difference is in the center of pressure, or the area in which aerodynamic forces act through. Some parts of the wing experience low pressure, and some parts experience high pressure. The center of pressure is the average of these pressure differences and affects the aircraft's aerodynamic balance and controllability. The diagram shows how the center of pressure moves on the wing for different angles of attack. When we talked about lift, we were talking about the lift caused by air flowing over the center part of the wing. If we look at the tip of the wing, there is a phenomenon that occurs known as tip vortices. When reaching the edge of the wing, there is still a low-pressure zone above the surface of the wing and a high pressure below. These pressure zones naturally want to even out, so the high-pressure air tends to flow towards the low-pressure air. The high-pressure area on the bottom of an airfoil pushes around the tip to the low-pressure area on the top. This action creates a rotating flow called a tip vortex. The vortex flows behind the airfoil, creating a downwash that extends back to the trailing edge of the airfoil. This downwash results in an overall reduction in lift for the affected portion of the airfoil. Manufacturers have developed different methods to counteract this action. Winglets can be added to the tip of an airfoil to reduce this flow. The winglets act as a dam, preventing the vortex from forming. Winglets can be on the top or bottom of the airfoil. Another method of countering the flow is to taper the airfoil tip, reducing the pressure differential and smoothing the airflow around the tip. We hope you learned a lot. Please help us spread the word about Pilot Training System, and we look forward to further servicing your flight training needs.